Hello, my name is Ron Kenneth. This is a joint talk with Chris Gottwald. We have two objectives in this talk. One is to introduce you to a novel methodology which consists of applying designed experiments methods to large language models. This is a very exciting and new methodology that can affect all of you here. The second objective is to show how JMP can be used in a seamless fashion to apply different analytic methods. This is an exceptional feature of JMP, and hopefully the combination of the two will motivate you to try out what we are going to show you. So there are going to be two case studies. A simple one that Chris will cover, and then a more complicated one that I will cover. So let's start with a very basic question. Who knows about DOE? And wow, many hands up. So a lot of people here know about DOE. Who knows about LLM? Let me move this a bit down. Okay, quite a few hands too. Who knows about DOE and LLM? So at this point, it's only Chris and me. Hopefully, by the end of the talk, we'll have more hands up if we ask the question. It's a new methodology, and it's based on prompt engineering experiments. And designed experiments started in agriculture, and these required long cycles and the complex patterns. Here we have very short cycles and a lot of unknown patterns due to the pre-training of these LLMs, which is based on billions of records. The way you interrogate the LLM is through prompts. These are affected by hallucinations. The stochasticity in these responses is controlled by something called temperature, and there is a filter called alignment that helps you keep the responses helpful, honest, and not harmful. We won't cover all these aspects of LLMs, but it's the combination we're interested in. And basically, there is a context. We put questions to the LLM and we get responses. So Chris will move on with the simple example. Chris, please go ahead.
Thanks, Ron. So the idea is to create a simulated survey, a set of prompts for an LLM where we ask it to give a first-person answer to the question, how often do you floss and why? We will also give it some background demographic information about who the speaker is. Now, this demographic information that we give the LLM consists of factor settings from a JMP DOE where we have factors for age, gender, education, and job category. The LLM will create text responses to these prompts in a format like an open response survey. Once we have all the responses in hand, we can return to JMP to analyze the results using Text Explorer and some other modeling tools. The important questions we want to answer are the results going to be meaningful? And do they confirm our intuition about flossing behavior? Because this is a topic that we should know something about already. To do this, we first make a DOE for our demographic factors using JMP. Then I set up a ChatGPT API account so that I could run the DOE with a Python script instead of manually. I told ChatGPT what I was trying to do, and it wrote the Python program that used the CSV file of factor settings to create and submit the prompts for me. Then I got the responses analyzed and interpreted them in JMP. I'm going to go over the analysis first, and then I'm going to go over how I got ChatGPT to do the work I didn't know how to do for me. I'll also share what I learned about how ChatGPT really works and how to get more realistic results from it. The first thing I did was create a full factorial design in the 4 demographic factors. Runs are cheap here, so there was no need to use a smaller design. I also asked for 8 replicates per combination of factor settings, which turned out to be very useful in understanding how ChatGPT works later on. We model the results in JMP just like it were a real open response survey. To keep things simple and show how easy it is to get interpretable results, I stuck with JMP defaults wherever possible in the analysis. All of the results reflect ChatGPT 5.2's idea of how subjects would respond, which is different from a real survey involving real subjects. So it isn't easy to quantify the generalizability of a surrogate survey, but sensible patterns emerge that would deserve follow-up after thinking through about what results we should act on. With just a little bit of work in Text Explorer, we identified these 10 topics in the responses. The two most dominant topics were related to flossing frequency. The first topic is subjects saying they were regular routine flossers, saying things like floss every night and routine at this point. The second topic was related to irregular, inconsistent flossing, with tokens like couple times a week, remember, unless, honestly, having positive loadings, and tokens indicating flossing 4 or more times a week, having negative loadings. The other topics were more about what motivates or prevents them from flossing. Comments from dentists and hygienists motivating flossing was the next topic, followed by a peace of mind topic. Then a forgetful, lazy, tired family of excuses turned up as one topic. The next topic was how much seeing other people, friends, or coworkers was a concern in their flossing. The next was future health concerns, not wanting expensive and painful dental problems later on. There was also a stuck food topic about getting food like popcorn stuck in your teeth. Healthcare workers brought up their work directly quite often, and more than any other kind of job category in the survey. The last topic was one about the benefits of spending a few minutes to floss being worth it for your health in the long run. So I got these results by launching the platform with the defaults, except for STEM for combining. Then I added all the phrases that occurred at least 10 times as terms. Then I did a latent semantic analysis just using the defaults. And from there I also did a topic analysis using the default of 10 topics. To label the topics, I used the loadings in the first table that I showed, but often that wasn't enough. So I used the topic scores plots and selected the documents with larger scores for each topic and read through the results to identify a common pattern. This is definitely subjective, but the pattern was generally clear from the loadings and the sample of documents that was strong in a topic. Here I've selected the responses with the largest values of the first topic. It is immediately clear that these responses are from routine regular flossers that floss most, if not all, nights before bed. We just repeated that for all the topics to come up with meaningful labels for each of them. Now I'm going to do a digression into what is a topic. Well, technically, it is an exploratory factor analysis, a rotated principal components analysis of the document term matrix. A practical way of looking at it is as combinations of terms with high and low correlation to one another. If we take the two most positive regular flosser terms, just part and floss every night, and the two most negative terms in that topic, try to floss and week, and look at them together, we see that just part and floss every night occur together sometimes, but never with week and try to floss. The strength of these associations, both positive and negative, are measured with the topic loadings. Another way to look at the topic analysis is as a single layer linear encoder neural network. So if we cheat a little and use principal components analysis on these 4 terms instead of factor analysis, the PCA eigenvectors or loadings become the weight that go to a topic score's hidden layer node. The X prediction formulas from the PCA platform give the weights of the autoencoder's hidden layer to its outer layer. Note that I'm ignoring the biases here. And this idea generalizes perfectly to when there are more than one topics analyzed. I'm making this connection because this simple model that is structured like a single linear hidden layer neural network is being used to obtain useful, interpretable information about the inputs and outputs of a large-scale LLM. I also like to make the methodological connection between the simple-minded classic bag of words approach that was state-of-the-art maybe 20 or 30 years ago to the super powerful generative text large language models that are wide and deep multi-layer perception networks made with tremendous computing power and decades of clever tricks, but can be seen as building on the same ideas as the old school latent semantic analysis on a bag of words. Now I'm going to model the topic scores using GenReg with forward selection applied to a full factorial model to see how the demographic factors affect the topic scores. Here's a profiler from the resulting model for regular routine flossers. The 0 line separates a positive topic score from a negative one. The factor settings for each of these plots maximize the predicted score. In this case, there is no relationship between gender and job with the routine flossing topic. Middle-aged people with associate degrees tend to score positively on regular routine flossing. For the irregular flossing topic, the most prominent pattern is that it decreases with age. There really wasn't a pattern that emerged between the factors and the dentist-motivated flossing topic. It seems to be affecting everyone equally. Peace of mind as a topic becomes much more common as people age and slightly with higher education. Being forgetful, lazy, or tired was mentioned less as people aged as well. The social life topic was when subjects mentioned seeing friends or coworkers as a motivator for flossing. I find it kind of unsurprising that this decreased with age. Interesting, the future health concern topic was less a concern also as people aged. I was quite surprised by this one. So apparently everybody gets food stuck in their teeth, with the exception of healthcare workers with graduate degrees. So actually, because there's only 80 to 120 words per response for each subject, we only have enough room for 2 or 3 topics per subject. So it's much more likely that healthcare workers mentioned other things in the space allotted to them and didn't have enough time to mention the times when barbecue got stuck in their teeth and they had to floss as a result. The healthcare topic was really only present with people that were actually healthcare workers, not surprisingly. Mentioning it increased with educational attainment, and also female healthcare workers seemed to mention it more often than men. The time versus health benefit topic was pretty much the same for everyone over 24 years old. So what are the takeaways from this? I can think of a couple. Dentists and hygienists really do motivate people of all kinds to floss, so they should keep that up. Older subjects mention peace of mind quite often. So if you're going to put together a commercial for AARP, you might want to emphasize peace of mind because that's something that resonates with people that floss. Younger subjects were more likely to be irregular flossers, but they were motivated by having to be around other people and concerns for future oral health. So if you're doing advertising towards younger people, you might want to touch on those topics. And healthcare workers seem to have their own set of topics, often mentioning how seeing firsthand results of oral hygiene was a motivator for them. Topic analysis explains variation amongst the columns, but doesn't directly categorize the rows, which is a separate question that is answered by clustering. So the next thing I did was use normal mixtures clustering on the topic scores to cluster the rows and went with the BIC recommendation of 4 clusters in the data. Here are scatterplots of the top 4 topic scores colored by the 4 clusters. I named these clusters routine, semi-regular, irregular, and healthcare flosser clusters. To name these clusters, I created and modeled 0-1 cluster indicator columns and analyzed them with GenReg using the topic scores as inputs and the binomial distribution as the response distribution. 3 of the clusters were strongly identified with a single topic. So the clusters strongly predicted by the routine flossing, irregular flossing, and healthcare topics were simply named after their leading topics. We see that the routine flossers generally had a variety of topics that were mentioned in those rows. I think it's a little funny that the irregular flossers were primarily citing stuck food as their reason topic, and the leading reason topics for healthcare workers were dentist motivation and social life, such as coworkers or friends. The 4th cluster was a little harder to label because it didn't have a strong topic associated with it. For this one, I looked at a sample of responses from that cluster and saw that these were pretty regular flossers that flossed more often than the regular ones, but not as often as the regular routine flossers. So I labeled these the semi-regular flossers. What happened here was these rows were in something of a hole that the 10 topics didn't pick up. It could be that there are more ways to express this idea of semi-regular flossing than we could easily capture in a single topic dimension. This would suggest that if we had worked harder to curate our text token set with better phrasing, stop words, and combining of terms, this signal could have emerged more clearly in the topic analysis than in the one that we just did. When we analyze the semi-flosser indicator with the demographic factors, semi-regular flossing seemed to decrease slightly with age and more so with education. The other cluster analyses were so similar to their corresponding topics that it was kind of redundant to report them. Overall, the only new information clustering gave us in this case was that it identified a cluster that wasn't apparent from the topics. Other than that, clustering didn't add a whole lot to the story in this particular study. Now I'm going to go through how I actually ran the survey. I used ChatGPT to do this. First off, I have to admit that I was a newbie to using AI tools and was also completely new to writing Python code. It was truly remarkable how easy ChatGPT made this for me. I started off by describing the idea of a surrogate survey, and ChatGPT said it would be a clean setup to do this, and it mostly was. ChatGPT offered a lot of guidance. It knows that this presentation was for a JMP conference, and it intuited that I would want to do the design and analysis in JMP and use a scripting language to run the survey by submitting the prompts and retrieving the responses into a CSV file. Sometimes ChatGPT went almost too far in its advice. I was very surprised that it talked about setting the prior variance of if possible effects in the custom designer when I was setting up this study. It had obviously been trained on JMP's documentation, but didn't have a practical sense of how often some of the options are used. I probably haven't used the prior variance option in the custom designer in 15 years, despite using the custom designer at least weekly most of that time. So getting runs was going to be fast and cheap compared to a real survey. So I was planning on just running a full factorial instead of a small custom design with if possible interaction effects. It wisely recommended using the ChatGPT API so I could use a Python script to run this survey rather than manually run the prompt hundreds of times. I had to go through a couple steps to get the API set up, and it cost me a couple dollars total to get all the responses, but it really made it very easy for me. I also didn't have Python installed at all, and ChatGPT was very helpful in getting that set up along with the Visual Studio Code editor on my personal Mac computer, which I also just got last fall, and I'm still very new to working on Macs as well. As I went, ChatGPT said to copy any errors into the chat and it would recommend fixes for anything that came up. There was maybe a total of a dozen issues I had to work through, from getting the API key I purchased to be recognized, to some Unix shell script problems, as well as some minor bugs in the Python code. The first fix didn't always work, but it never took very long to fix the errors and bugs I encountered just by copying the error into ChatGPT, and it would always just tell me what to try next. Once I got it all working, I asked it to explain the Python code in detail. ChatGPT gave an excellent, clear explanation of the code it created at just the right level for me. It knew that I have a lot of experience with C++, so it made the similarities and differences clear without explaining basic concepts like if statements or looping structures. Here are some of the responses that I got. I was a bit disappointed that there was so much repetition in the responses. You can clearly see the identical text in adjacent rows. And if you read beyond that, you'll see that it's often just a restatement of the same thing from subject to subject. I felt that for this to be a useful approach, we would need to generate more variability in the responses. And to do that, I started off by asking GPT how it forms responses to prompts. How it works is it processes the prompt and generates a small collection of tokens, which are words or short phrases, that it deems are the most likely response tokens. The likelihood of a token is measured by a z-score. It then creates a conditional distribution of the tokens by combining those token z-scores with a temperature parameter that indexes how much randomness will be in the selected set of tokens. Then, a subsample is drawn from the tokens using this conditional distribution, and these are formed into grammatically meaningful responses. The temperature parameter is very important in that low temperature values lead to essentially the same response every time, which is useful when you just want a fact-based summary. Higher values of temperature will give you more varied responses, which is useful when you want a more natural human-like response or when you want more creativity in the responses. The key thing, though, is that the set of tokens is fixed and determined by the tokens in the prompt. How it works is it processes the prompt and generates a small collection of tokens, words or short phrases, that it deems the most likely response tokens. The likelihood of a token is measured by a z-score. It then creates a conditional distribution of the tokens by combining those token z-scores with a temperature parameter that indexes how much randomness will be in the selected set of tokens. Then a subsample is drawn from the tokens, and these are formed into a grammatically meaningful response. The temperature parameter is very important in that low temperature values lead to essentially the same response every time, which is useful when you want a fact-based summary. Higher values will give you more varied responses, which is useful when you want a more natural human-like response, or you want more creativity in the responses. The key thing, though, is that the set of tokens is fixed in that it is set deterministically from the input prompt. What this means is that the subject construct itself is just a set of tokens with a probability distribution over them, and submitting the same prompt multiple times is generating answers from the same population of tokens. If you give ChatGPT a prompt asking for it to generate a response that a female healthcare worker would give to the question, "How often do you floss and why?" it first breaks that prompt down into a set of input tokens, which we see here on the left. Then it generates a set of output tokens that it deemed most likely to be relevant to the input tokens. So we see these here now on the right. This set of output tokens will be fairly constant anytime the same version of the LLM is given those input tokens. In our case, suppose those output tokens are work in healthcare, floss every night, gum disease, and overall health. If you choose a low temperature setting for the response, the most relevant tokens will almost certainly be in the response, and the rest of the relevant ones will be excluded. The response will be fairly constant if the prompt is given repeatedly, saying things like, "I floss every night because I work in healthcare," basically every time. If a higher temperature is chosen, the same set of tokens will apply, but the distribution will be made more flat, allowing more variation in the responses, leading to responses like, "I floss every night. Since I work in healthcare, I've seen the results of gum disease on my patients." Or, "I floss every night because I take my overall health seriously." On the left here is the actual math used to combine the token z-scores and the temperature parameter to create the token distribution. When I asked ChatGPT about recommendations for temperature setting, it gave me the recommendations on the right, saying essentially that values of 0.7 to 0.1 are useful for creating human-like responses. So in the survey, I used temperature equals 0.9 to generate our responses so that they have variety, but stayed away from the far upper end of the recommended temperature. For the initial survey design, higher temperature didn't help very much. So the question then became, how do we make the token population be different from subject to subject and less like asking the same person the same question multiple times? I wanted a way to create more diversity in the responses, but wanted it to reflect human reality, to be easy to generate a distribution for, and without adding more demographic factors. What I ended up using is called the Big Five for personality traits, which are a factor analysis that describes human personality in 5 dimensions that has been confirmed and validated many times over the years in different populations and is fairly stable across age. The 5 dimensions are openness to experience, which measures creativity and curiosity, conscientiousness, measuring self-control and diligence, extroversion, which measures boldness and how much social interaction you prefer, agreeableness, which measures kindness and helpfulness, and neuroticism, which measures anxiety and depression. If you take a personality test, it will give you percentile rankings on each of these dimensions, and these dimensions are approximately independent of one another. The idea here was to generate random Big Five percentile scores for each subject and have the prompt include information in a way that ChatGPT can take into realistic consideration. The data analyzed at the beginning of my talk used the Big Five as latent factors to generate the responses, but we ignored them intentionally in the analysis. This emulates how survey data is generated and analyzed in practice more closely than either ignoring them in the generation process or including them in the analysis. I asked ChatGPT if this was a good way to increase variability, and it strongly seemed to think so, and it also seconded my inclination to not include the scores in the analysis. I also asked if the original study was like asking the same person the same question repeatedly, and adding personality scores would make it more like asking different subjects, and it also agreed. It gave a detailed comparison, essentially saying that the speaker construct was the set of tokens summoned up by the prompt, and that having different speaker prompts changed the tokens and their generated distribution. I proceeded to ask it to create a new Python script that would accept personality scores in the design table. I generated the personality scores from a uniform random distribution. In another chat, it explained that there is no Big Five construct within ChatGPT, only input tokens that generate a response token distribution that are conditioned in a way that aligns with text responses consistent with those real personality traits. The Python script it created mapped the Big Five scores into prompts that reflected the anticipated communication style of the personality traits for me. The results of these extended prompts was that it generated response tokens and a distribution that reflected how someone with those Big Five personality scores would likely respond. Here's an example where the subject replicate has been augmented with personality scores that have been translated into prompts to tell ChatGPT the communication style and preferences of the subject. This subject has a conscientious score of 46, and that got mapped into a part of the prompt saying the individual would communicate some routine, but not rigid, and generally tries, but isn't too consistent. Comparing the same subject responses that were generated without personality scores on the left and with them on the right, we clearly see that there is less replication in the responses with the factor scores than without them. I did a side analysis of the topic scores using the personality and demographic inputs, and the latent personality scores were generally the most predictive of the topic. The actual analysis where I left these out was what you saw earlier in the talk. We can see the difference by focusing on the female healthcare workers, comparing the most common terms from the no latent factor dataset to the subsets of the final dataset where the conscientious score was in the upper and lower third of its distribution. The set of tokens and their distributions are more similar between the no latent factors case and the high conscientiousness case. Interestingly, work and healthcare is the number one term in the first two, but drops off entirely in the low conscientiousness case. This is sensible, as why would someone that flosses less regularly cite their job as something motivating them to floss? Floss every night is also common in the first two, but drops out in the low conscientiousness case. On the other hand, the low conscientiousness case has terms like honest, remember, try, sometimes as frequent terms, which were indicative of less routine flossing in our analysis. Overall, we can clearly see how the token distribution is changing and becoming much more diverse with the addition of the latent factor scores. So this concludes my part of the talk. To recap, we generated a DOE with demographic factors as a surrogate survey. To get more realistic subject-to-subject variation in the text, we used Big 5 scores as a part of the prompt. ChatGPT made it very easy to write and run a Python script that ran the prompts and accumulated the responses into a CSV file. Overall, this was easy to design and run and was done without any major effort to curate optimal results. Now I'll hand it over to Ron, who's going to go over a more realistic, larger example. Go ahead, Ron.
Hello again. Thanks, Chris, for the case study, which introduced the approach, the methods. Now I'm going to go through a more elaborate case study. It's a collaborative project with social scientists. Their interest is in, and their specialty is in what is called resilience. Resilience is how people react to disasters and what's their ability to recover after a disaster. They sat down and listed 13 factors that could affect resilience. The time frame from event, the distance of the event from the respondent, the location, the occupation of the respondent, family status, age group, gender, religion. And based on these factors, factor level combinations were designed with custom design, 13 factors, 128 prompts. In this case, the number can be much bigger because there's really no effort in generating the experiments. These are actually simulated. You can think of that as a simulated survey with individuals that are profiled with these 13 factors. And we had 128 prompts. The custom design balanced the values, the levels of these factors, so it was pretty balanced. It basically filled the space of the different factor level combinations that we got in these 128 experiments. For each of these prompts, we got a response. There was a small application developed that uses the LLM API to derive the response. They cost a few cents each of them, so this is pretty inexpensive. And now this set of responses was fed into the text explorer. This is the term frequency analysis that you get from the text explorer. 128 listings, 588 different terms, which means words. Resilience was the most common one in the responses that we got from the LLM, 404 times. Political was 154 times, education 135 times. These terms are used with Latin class analysis and to basically a reduction of the data of the document term matrix to generate topics. These are the latent topics. 10 topics are basically describing the 128 responses. The experts labeled them by looking at the loadings of the terms that identify the topics. The first topic was labeled multiple factors. This is several, influenced, factors, mix. That's why they call it multiple factors. Topic 4 was children, married, family, emotional. This was labeled family status. And we have a score for each prompt response in terms of these 10 topics. So we can go ahead and analyze these scores. On topic 1, the generalized regression showed us that political tendency of the respondent had an effect 1.66. So it was a pretty high effect on the topic 1 score. We had 11 factors that showed up in the lasso analysis that we did, and you can see the effect of the political tendency through the profiler. If you look at left, they are more belonging to topic 1, their responses, than center and right views. Topic 4, the family status. Okay, so family status, is this a bachelor or a married individual, was what determined what had the highest effect on the family status topic. We had 8 factors there. Between bachelor and divorced, we didn't see any difference, which was a bit surprising. And between married with children and without children, we didn't see differences. So this was a curious insight that the domain experts continued to debate, and that was eventually had a sort of surprise effect on their understanding. The other thing that was done is to combine the 10 scores using an overall measure, which was calculated through the T-square multivariate control chart approach. T-square is the Mahalanobis T-square, very easy to do. So now we have 128 runs, which are determined by 13 factors, and that gives us the Mahalanobis T-square. If we look at the T-square, we see some prompts that stood out and some prompts that were above the upper control limit, and then all the rest. We did the in-depth analysis, and when we did the generalized regression analysis on the T-square, nothing turned out significant. 6 factors showed up in the lasso after feature selection, and it was all flat. So to wrap up, we talked about designed experiments. We talked about conducting text analytics on the responses of these experiments. We showed how to apply penalized regression lasso model to see what affects the topics in terms of the factors, what are their effect on the topics that came out from the text explorer. And we provided an overall view of what's going on with a T-square analysis of all the topics. The conclusions that the experts listed are here. One is they emphasize that this study was focused on personal resilience. Other studies that were conducted looked at resilience of a community and national resilience. Here we showed personal resilience, that text analytics generated by ChatGPT 4.0 responses was carried out with JMP, very easy to do. We found that the left political tendency had higher effect on multiple factor topic compared to center and right. This was interesting, but not unexpected, I guess. We found that bachelors and divorcees have similar effect on family status topic. That was surprising. And we found that no factor affected all 10 topics as assessed with T-square. So here you go. We had a topic to look into. We designed the experiments, we ran them, we analyzed them, and we came up with findings. Obviously, we are here to answer questions. Thank you for your attention.